Okay, so in the today's class we will be seeing about the next topic, the next type of flip-flop, which is called as T flip-flop. So here T stands for toggle flip-flop. Okay, so the next flip-flop what we are going to see is nothing but here T flip-flop. Okay, so here T stands for toggle flip-flop. Okay, so in this T flip-flop, here also we are going to work on only two states. Okay, so first of all, why this T flip-flop, then we will see about the logic diagram or your circuit diagram, then the operation of the T flip-flop, which will be followed by the extended truth table. Then we will go about our characteristic equation for this, and finally we will be seeing about the excitation table for the conversions. Clear? So the first part is nothing but why this toggle flip-flop. So in the toggle flip-flop, if you want a complementary operation, that is set and the reset in for the complementary inputs, then we are focusing on this toggle flip-flop. In the direct flip-flop, I got a direct outputs, whereas in your complementary, based on the input as 0, I will get a complementary next state as 1. If the input is 1, I will get a complementary next state as 0. So like that way I want to get my output, which means that if I give 1 is 0, I want to get your set output, and if I give 1, I want to get my reset output. So this is the condition behind this T flip-flop. So how to draw this T flip-flop? So drawing of your T flip-flop is a advancement of your JK flip-flop. So how we will draw our JK flip-flop? So JK flip-flop, that is sorry so this output is nothing but the feedback over here. This output is nothing but the feedback over here. This is nothing but Qn bar. This will be nothing but Qn. The next state is nothing but Qn plus 1. Here the next state is nothing but Qn plus 1 the whole bar. And one more thing we are going to connect over here, and already we know that here it will be connected with one more NAND gate, and this output is going to come as the input for this. Okay, and this output is going to come as an input for this, which means that Qn bar will be here, same Qn bar will be here, and here I am having here Qn, and here also another output will be Qn, and we will have one more input as your clock, which is nothing but 1. Clear? And one more input. So here instead of giving us a 2 separate input, I am combining these things and I am going to give us a single input, which is called as a T input. Clear? So this is the normal circuit diagram of your T flip-flop, and I am numbering the T flip-flop as 1, 2, 3 and 4. Now if there is a single input, already we know that there will be only two combinations. Either it may be a 0 or it may be 1. So what will happen when the input is 0 and what will happen when the input is 1? Okay, and you ensure that here you have connected input T directly to the gate number 1 as well as 2 without making any complement thing. Okay, so what will happen when T equal to 0 and what will happen when T equal to 1? So this is nothing we are going to see now. So now I will start with the first operation, that is T equal to 0. If T is 0, one of the input will be 0 over here. Here also one of the input will be 0 over here. And already we know that if any one of the input for the NAND gate is 0, I don't need to worry about the other gates. Automatically the output will be 0 into anything 0, 0 complement, you will get the output as 1. And here also I will get your 0, your output as 1. So I will get your output as 1. So now when you check for your Qn plus 1, you see Qn plus 1. So your Qn plus 1 is nothing but 1 into Qn bar, the whole bar. So which is nothing but Qn. Okay, and similarly on the bottom side also I am getting, that is Qn plus 1, the whole bar is nothing but and 1 into Qn bar, the whole bar is nothing but Qn bar, the whole bar. Okay, so here what is happening? So when T is 0, whatever the present state is there, that will be coming over here directly. Okay, so whatever the present state is there, that will be coming directly when T is 0. Now we will change the next condition, that is when you make your T as 1, that is when T is changed into 1, what will happen? So now the input on one of the gate is 1, here also the input will become 1. So if it is like that way, what will happen? So now you want to check for the output at gate number 1. So output at the gate number 1 is what? 1 into Qn bar, so which is nothing but Qn. Similarly, if you see output at gate number 2 is nothing but 1 into Qn, so your output will be Qn bar. Okay, similarly your output at Q3, which is nothing but Qn plus 1. So output at Qn plus 1 is nothing but what? So one of the input is here Qn, other input is Qn bar, the whole bar. And similarly the output at Q4, which is nothing but Qn plus 1, the whole bar. Here it is nothing but it is on the Qn bar into Qn, the whole bar. Clear? So now if you see, Qn plus 1 is nothing but Qn into Qn bar, the whole bar, and Qn plus 1, the whole bar is nothing but Qn bar into Qn, the whole bar. Okay, so now like our previous thing, what I am going to do is, when Qn equal to 0, I am proceeding at the top side. So at the top side what you will get? Qn plus 1 equal to 0 into anything, so it will be 0, so 0 complement, I will get the output as 1. Okay, so now when Qn equal to 1, I am proceeding at the bottom side. Bottom side what will happen? Qn bar will become 0. Okay, Qn is 1 means Qn bar will become 0. On the bottom side, if you write the equation for Qn plus 1, if you substitute, this also will become into Qn, once again 0 complement is nothing but 1. Okay, so what is on the gaining here? So you are getting Qn plus 1 bar equal to 1. So which means that what is your Qn plus 1? That will be equivalent to 0. So when this is becoming 0, when Qn equal to 1, my Qn plus 1 is becoming 0. And when Qn equal to 0, your Qn plus 1 is becoming 1. Okay, so that is the indirect meaning. That is Qn plus 1 equal to, that is Qn equal to 0, Qn plus 1 is becoming 1, and qn equal to 1, your qn plus 1 is on the becoming 0. So which means that present state is on the complementing. Okay, so when I write in the time of on the truth table, so this will be your t, this will be your qn, and next thing is here qn plus 1. So t is 0 irrespective of the present state, and my next state is your present state. But t equal to 1, your present state is nothing but complement of your present state. Next state is nothing but your complement of your present state. Clear? So this is the thing. Now we are going to explain this in a form of an extended truth table. Okay, I am going to explain this in terms of your extended truth table. Okay, I am going to explain this in terms of your extended truth table. So extended truth table means one is nothing but your input, which is nothing but your t. So t can be either on the 0 or 1, and similarly your present state, that is qn, can be either 0 1 for t equal to 0 and 0 1 for t equal to 1. And now we want to find here on the next state, which is nothing but qn plus 1. So what is happening qn plus 1? When t is 0, irrespective of your present state, when t is 0, the present state is retaining as such. So whatever the present state, so you can see here, when t is 0, the present state is retaining as such. The next state is nothing but your present state. Okay, next state is nothing but your present state. So next state is what? Your present state. And when t equal to 1, what is your on the next state? When t equal to 1, your next state is present state complement. Next state is present state on the complement. So if present state is 0, this will become 1. If it is 1, this will become 0. And next state on the complement. Okay, so this is nothing but my extended truth table. Okay, this is nothing but your extended truth table. Present state is becoming complement. So using this extended truth table, now I am going to write here a logic expression. So this is your logic expression, otherwise also called as characteristic equation. Characteristic equation. So characteristic equation for qn plus 1. So here also there is a single input. One of the input is t, other input is qn. Qn can be either 0 or 1. T can be also either 0 or 1. So where you got your output next state, when t equal to 0 and q equal to 1. When t equal to 0 and q equal to 1, my output is 1. Similarly, when t equal to 1 and qn equal to 0, t equal to 1 and qn equal to 0, my output is 1. So here we have a diagonal pairing. So if it is a diagonal pairing, how we can write qn plus 1 equal to t XOR of qn. This is your diagonal pairing concept. Otherwise, if you are unaware of this, we can on the group like this way also say single. Okay, this is your t, this is here on the qn 0 1, and this is 0 1. Here I am having here 1. So this is one thing, this is one thing. So for this, the answer will be something like t bar into qn, and for this the answer will be something like this is nothing but t bar into qn, and this is nothing but t into qn bar. So once you write your next state qn plus 1, this is nothing but t bar into q1 plus t into qn bar. Okay, so this is your next state. Now we can check with the condition also, that is, for example, when t equal to 1 and qn equal to 1, what will happen when t equal to 1 means your present state will get complemented, that is your qn plus 1, it should become qn plus 1 should become as 0. Okay, so now if you substitute your qn plus 1 equal to what you will get, then this will be 1 complement into 1 plus 1 into 1's complement. So this will be 0 into 1 plus 1 into 0. So finally you will get us 0. So what is happening? Here if we make your qn as 1, your qn plus 1 is becoming 0. You can check for other one condition, that is what happened when t equal to 0 and qn equal to 1. So t equal to 0 means your present state will be retained as such. Okay, so it will be qn plus 1 equal to t bar into qn plus t into qn bar. So t bar, that is t bar equal to 1, that is 0 bar into 1 plus 0 into 1 bar. So this is nothing but 1 into 1 plus 0 into 0. So finally you will get us 1. So what is happening when t equal to 1, whatever the present state is there, your next state is also repeating the same thing. Okay, next state is also going with the same operation. So now using this extended on the truth table, now we are going to derive the final thing, which is nothing but your excitation table. Okay, when you talk about the excitation table depends on your, already we know that it depends on your present state, next state. Based on that I am going to find your mandatory input t. So your present state and next state, either it can be 0 0 0 1 1 0 or 1 1. We want to check where you have this particular condition. So I will go with the other color. So first thing is 0 0, where you have your present state as 0 0. So for 0 0 the mandatory input is 0. For 0 1 the mandatory input is 1. For 1 0 the mandatory input is also 1, and for 1 1 the mandatory input is 0. Clear? So your present state. So this is my characteristic equation. So where you will get 0 1 1 0. So 0 1 1 0, that is your excitation table. So this is with respect to our T flip-flop. So we will once again refresh what we have started with our T flip-flop. So T flip-flop generally stands for toggle flip-flop. Toggling means your present state is going to get toggled based on the value of your t. That is, if t is 0, your present state will be retained as such at the next state, whereas in your when t equal to 1, your present state get toggled from 0 to toggle based on your present state. When t equal to 1, your next state get toggled based on your present state, which means that when t equal to 1, if your present state is 1, it will become 0. When t equal to 1, if present state is 0, your next state is going to become 1. Okay, so why this means, in order to have if you want to have a set condition and reset condition, and that to complement the set condition and reset condition for your inputs when t equal to 1. So first we have explained about our logic diagram or the circuit diagram. Okay, where the diagram is similar to here JK on the flip-flop. The only difference here is, in our JK flip-flop I will be having a separate on the lead for making a connection, But here instead of having a separate lead, we are connecting both here and the j k inputs to a common node at the common point. So both here j and k are connected to a common point. So you can see over here how both j and k are connected using a j and k are connected using a common point. Okay, and so when your t is becoming 1, the same value of t will be going to the gate number 1 as well as to the gate number 2. Okay, and when t equal to 0, the same 0 value will be going for the gate number 1 and gate number 2. And already we know that gate number 3 and 4 are cross coupled on the configurations. Okay, cross coupled configuration, which means that the output of 1 will be going as an input for the corresponding opposite. Similarly, the output of the corresponding opposite will be giving us an input for the next one on the top side. Okay, so now if you make when t equal to 0, what will happen? So when t equal to 0, already I told you that one of the input is 0, definitely the output for the particular gate will always become in 1 if it is an AND gate. If it is an AND gate, the output will be definitely it will be 0 if any one of the input is 0 condition. So since it is the complement, so we are on the getting the we are getting your output in the corresponding on the fashion. So now for your input as on the 0, I am getting my output at the gate number 1 as 1 and gate number 2 also as 1. Okay, and the gate number 2 also has 1. So this 1 and 1 will be feeding over here, and I have explained in this on the point you are getting this structure. Okay, but when t equal to 1, what will happen? So 1 into 1 into qn bar, so here the output will be qn, and the same way at the bottom side also 1 into 1 into qn, bottom side you will get the output as qn bar. So here when you talk about your qn plus 1, it will be having qn into qn bar. At the bottom side qn plus 1, it will be having like qn into qn bar, whole bar. So both the equations are looking on the similar, but there is a huge on the difference when you make the present state as either 0 or 1. So in order to make the present state as on the 0, my next state what you got is nothing but 1. Similarly, in order to make it on the present state as 1 over here, okay, as 1 over here, your next state I am getting here as on the 0. But how to proceed this part alone? So when your present state is becoming on the 1, automatically we are on the propagating at the backward side, the ground at the bottom side, because with the 1 I cannot on the find the value, so somehow one of the input should be a 0. So what I am on the doing is, instead of propagating with the same qn as 1, I am propagating with the qn bar as the 0. So both are on the same only. Instead of propagating with the qn as 0 1, I am propagating with the qn bar as 0. So this will become on the 0. So if this is 0, definitely at the bottom part it will get as 1. Okay, so if bottom part is 1, definitely what will be your qn plus 1, that will be a 0. So for qn equal to 0, I am getting as next state as 0. That is qn equal to 1, the next state is 0. And qn equal to 0, the next state is giving 1. Okay, so based on that we have on the written as if present state, that is when t equal to 1, and your present state is on the complementing as complementing. Okay, so that one we are writing in the term of expanded on the truth table. Okay, if present state is 0 and t equal to 1, okay, the next state is nothing but the complement of the present state. And when t equal to 1, if the present state is 1, it will become on the complemented to 0. But for the normal thing, there is no change required. Okay, when that is when t equal to 0, whatever the present state is there, that will be coming in my output condition, that is in the next state condition. Whatever the present state is there, that will be coming in your next state condition. Next state condition. So based on this extended on the truth table, we also have written our excitation on the table. So where the excitation table is given by where the excitation table is set by your present state and the next state. So based on your mandatory inputs for your present state and the next state, what will be the mandatory input? Okay, so based on your present state and the next state, what will be your mandatory input conditions? And similarly, we have find the characteristic equation that is for our T flip-flops. Okay, so now we have come with the final stage. So in the complete last 4 lectures, we have started with the 4 different types of flip-flop. One is here SR, then we have seen about what is called as on the D, then we have seen about what is called as on the JK, then we have seen about what is called as T. Okay, so these 3 flip-flop, 4 flip-flop we have on the scene. So when you talk about this SR, okay, SR flip-flop, we will make one consolidated on the table over here. So what is here on the SR flip-flop? What is the consolidated table over here? So in your SR flip-flop, okay, so in your on the SR flip-flop, what is the next state equation? So in your SR flip-flop, you see the next state equation is S plus R dash into Qn. S plus R dash into Qn. So S plus R dash S plus R dash into Qn. So here what is here on the next state? So here the next state is nothing but your present state, that is Q. In your JK, what is the next state? JK is J into Q dash n plus K dash into Qn. And here the T flip-flop, the next state is nothing but TXR of your present state. This is your next state. Okay, and when you talk about the excitation table for your on the SR on the flip-flop, this is most important, that is Qn plus, and what will be your mandatory S and R. If you see, simply I told you, you write the things, that is 0 0 0 1 1 0 and 1 1, and you replicate this directly, and here you put as X, and this will be X 0 1 0. Okay, but for here, that is for your D flip-flop. So what is here on the D flip-flop? 0 0 0 1 and 1 0 1 1. So D flip-flop, the next state and the present state are same, 0 1 0 1. You will get it here. And in your JK flip-flop, that is Qn plus 1, and what will be my J and K? So 0 0 0 1 1 0 1 1. So here the first bits, 0 1 will be coming same, and he will mention here as X and X, and here once again in the X and X, and this will be 1 0. So this will be your excitation table. So everything is with respect to your excitation table you are writing. And here when you talk about this thing, okay, that is Qn plus 1 for the T flip-flop. So this one 0 0 1 1 0 1 1. So here it is 0 1 1 0, because now right now only we have on the scene, it is nothing but 0 1 1 0. Okay, so here it will be 0 1 1 0. So this excitation table, all the 4 excitation table and the truth table should be known very well for each and everyone. So what is the truth table? Truth table is very easy. That is, we write the shortest truth table. SR, here it is nothing but Qn plus 1, In our SR, what it is on the happening? In our SR, it is 0 0 0 1 1 0 1 1. Okay, so and irrespective of here present state, so this will be nothing but your present state. For 0 1 it is 0, and for 1 0 it is 1, and this is your indeterminate form. And when I talk about here on the D flip-flop, okay, D flip-flop, and what is my next state with respect to here Qn. Okay, so D is 0 and irrespective of thing, or 1 irrespective of thing. 0 means your next state is also 0, 1 means your next state is also 1. Okay, similarly the next thing is here JK flip-flop for your Qn and Qn plus 1. Qn plus 1. So JK 0 0 0 1 1 0 and 1 1. Okay, and first we will give it. So here 0 0 means same thing, here present state will be coming there, no change. For 0 1 it is 0, for 1 0 it is 1, for 1 1 the present state is giving complement. And in the T flip-flop, what is happening? For Qn and Qn plus 1, Qn plus 1, if it is 0, I will get your output as whatever the present state, that will be your output. If it is 1, the present state will get complemented. Okay, so this is the complete truth table, that is shortest form of truth table. So this is your truth table, and this will be your excitation table. Okay, so this complete tabulation, that is for SR, JK, D and T, what is my next state, what is my excitation table, and what will be my truth table. Each and everything we want to keep it in the mind while we are drawing the things. And SR, it is SR flip-flop is nothing but extended version of your SR and the latch, where you are using a clocked SR and the latch. So in the your SR latch, if the input S and R are connected through a NOT gate, you will get your D flip-flop. And in the SR on the flip-flop, if the third and fourth gates, that is the output on the gates, the feedbacks are on the connected to the input on the side on the gates, then in a form of cross-coupled configuration, then we will get our JK flip-flop. In the JK flip-flop, if both the inputs J and K are connected on the together, okay, or J and K are connected or together, then we will get our T flip-flop. So in the block diagram, okay, so S R, this will be Qn, this will be Qn bar. Okay, and output is nothing but Qn plus 1. Next state is on the Qn plus 1 bar. So here I am doing nothing, and you can have one on the clock pulse over here. Okay, so the next what we are on the doing is the same thing. Now I am on the connecting both the inputs and going to give one input as on the D, here Qn, same on the Qn bar, here Qn plus 1 and Qn plus 1 the whole bar you will get. And in the JK, internally it will get on the differ. Okay, this internally it will get differ, that is the feedback of your first should be given for the next, like that way cross coupled feedback will be given. Clear? So I think all of you may clear with this on the flip-flop. So in our next class we will see about the conversions. Okay, conversions. So I told you there will be nearly 12 conversions. We will start each way. First we will start with what is our SR, how to convert your SR to D flip-flop or JK flip-flop or T flip-flops. Okay, in the similar fashion we will see about the conversion of the D flip-flop to SR on the flip-flop, JK flip-flop and T flip-flop and so on. So I thank you once again all for your patient listening of this session. We will see in our